Right, so hi everyone, welcome to the Grothendix School. This is the third lecture on the topological K-theory part of the K-theory in totality series. In today's lecture, we're finally going to define what K groups for topological spaces are. In the next section, we are going to see some further developments in that, in let's say Bott periodicity and stuff, and eventually concluding the topological K-theory part with K-theory as a generalized homology theory. But that's a long time goal now. So let's start to this lecture. Dr. Mohit, you can start.
Thank you, Dipankar. So let me first recap what we had done before. Since it directly links. Nice. So first we saw that isomorphism classes of vector bundles were some kind of a homotopy invariant. So the one critical lemma that we saw was that given a homotopy, right, ft, right, then we'll have, if given such an homotopy and a vector bundle E on X, then f upper star of T was in fact, f upper star of 0 was in f upper star 0 of this, f1 upper star of E. These were isomorphic vector bundles. Furthermore, we also note that this pullback operation that we have preserves direct sum and tensor products, right? So what we are saying is that f naught upper star of E direct sum f is actually E direct sum f upper star f. And so it's some kind of a ring homomorphism. That's what we're really saying. E tensor f is f upper star of E tensor f upper star of E. Another thing that we saw in the first lecture, which we'll finally use, is given a exact sequence of vector bundles, that is an injective map, injective on fibers, followed by right a surjective map, such that the composition is there. Right. So given an exact sequence of vector bundles, we know that such exact sequence always splits, right? Right. So that's another fact that we noticed. Now, and lastly, we then, right, I'll write it in the same page. So last thing that we saw and was that so what we can already see using this homotopy invariance of isomorphism classes of vector bundles is that that's a homotopy invariance. And so as a matter of fact, we managed to classify vector bundles on the suspension of X to be X, comma, GLNC, right? Of course, this is when the field is equal to C, right? So all vector bundles can be made over real or complex, right? But this particular lemma that we stated is for complex only, right? So, right, for complex vector bundles. So now, if it's possible to do it for suspension, one kind of obvious question is, can we do it for just X itself, right? So that's how we begin today, classifying spaces. So the aim is to give a similar criterion as we just saw give a homotopical criterion for vec nx, right? Like we previously did it for suspension. Now we are asking, can we do it for can we directly do it for x? So that's the aim. And so we'll start by preparing for the main statement. So first is lemma. E be a vector bundle over x. Then there exists a trivial vector bundle x cross w and a surjective map x cross w to, right? The proof, choose a finite cover. Right, right. Again, one underlying assumption that I want to recall is that all our spaces, we took it to be compact Hausdorff so that the proofs are simplified. These things can certainly be extended to general spaces, but most of the technical, most of the intuition I feel like can be seen in compact Hausdorff itself. Like pushing these results to other spaces like locally compact is certainly possible. Right, but we'll just assume that these spaces are compact Hausdorff. So choose a finite cover over U alpha on which E is trivial. Right? Right. And so that means E U alpha, E restricted to U alpha is isomorphic to U alpha cross V for some V. Right? So choose a basis of the sections. Choose a basis of V, say EI, right? And actually EI comma alpha, because of course V also depends on U, so we're choosing that. Actually, yeah. So EI, and so we'll get sections of U alpha cross V given by basically X goes to X cross X comma EI, right? So this section we're going to call EI alpha, right? So EI alphas are the section which send the point X to X cross EI, X comma EI. So now for every U alpha, we can choose such sections, right? Now we define EI alpha bar to be a section from X to E, right? Which is defined by sending, say, a point X, which is basically defined by EI alpha bar is EI alpha times a bump function, right? So these functions were like one on, say, a compact subset, and then they taper off to zero outside of U, right? So by multiplying with this, we can just extend the whole function to x, whole section to x. And now what we do is we look at this function x cross w to, so w is the vector space of generated by EI alphas, right? So EI alpha bar. So now we define a function from x cross w to E given by x comma section. Any element in W looks like a section. This maps to x, no, wait, the section evaluated on x, right? We claim that this map is surjective, and that is primarily because if you take any point, it must lie in one of the points of this cover. And as soon as it lies in one of these points, we have this basis that we chose for that cover, and this point will therefore just be a linear combination of those spaces. So now I'm just going to write. So that kind of gives an argument of why this is surjective, right? So this is the surjective. So any questions? Actually, I'll continue writing here. So corollary. If E is a vector bundle over X, then number one, there exists X cross W such that E is a subset of this trivial bundle X cross W. So let's just see how we can get this. So notice that there is some trivial bundle which surjects onto E dual as well. The moment we dualize this surjection, we'll get that E is injective in some trivial bundle. So that's the proof. Number two, there exists F vector bundle over X such that E direct sum F is trivial. So we know that E sits inside X cross W, right? And we can always quotient, if it's a sub bundle, we can quotient it. But we also know that exact sequence is split, right? We just recalled that. And so the quotient that we got is precisely the vector bundle which will have the property that E direct sum F is trivial. So any questions still here?
Yeah, so Pawan is asking, can you say something about rank of W?
Rank of W. So the way we have constructed this is very big, but one obvious dimension that we are getting is that, so the number of U alphas, which is a finite cover, right, times the rank of E. So that's clearly a number that we are getting. But we have no real control over what is the size of this cover. So we don't really know. We don't have full control over W, but we can say that W is of dimension, the number of covers, like the size of the cover, the finite cover that we had, times rank of E. Right. Anything else? So Grassmannian. So I'll define the Grassmannian. I think most people know what it is, but we'll still do it, right? So if V is a vector space over F, then then we define G R K comma W to be K dimensional subspace of W, and G R K comma N to be G R K comma F. Recall that this F can be both, it could be either real or complex. So we're doing it in such generality. So now we have just defined this as a set. So what one can argue is, how do you topologize the Grassmannian? So for topology, fix, right, fix an inner product on W, right? Then what we know is that K dimensional W, this is in bijection with rank K projections, orthogonal projection on W. Right? So that means what we have obtained is a map from GR K comma W, an embedding of GR K comma W to endomorphisms of W, right? And we assign the Grassmannian the subspace topology. Okay, so one thing to check is that this topology happens to be independent of the inner product, which I leave as an exercise, right? So now there is this one very important vector bundle on the Grassmannian called the tautological bundle. Tautology. And roughly what tautological bundle is it will be a vector bundle over, right? So I'll T for tautological, so I write T over Grassmannian K comma W, right? Such that TP T of some subspace K, maybe not K, all right? T of K is equal to K, where K is a subspace of W, right? K dimensional subspace of W. So that's kind of the idea. The definition of T is therefore just it is by definition kernel K comma P belonging to Grassmannian K comma W cross W such that P belongs to K, right? And the map to the Grassmannian that we take is just the second projection, like the first projection. Right, and now one can check that the inverse image of the point capital K in the Grassmannian is the vector subspace K itself. So in some very weird sense, what we have done is that we have said, okay, Grassmannian is set of, like, a point in Grassmannian is a K-dimensional vector space. The vector space we want to attach to that K-dimensional vector space is itself. That's what the tautological bundle is. The vector space above the point K is K itself.
Doctor, sorry to interrupt. Can you drop the Jamboot link to the chat?
Oh, sorry, I forgot. Sorry. Share. I'll have to do a bunch of things. With the link. Viewer. Yes, that's fine. Copy link. Link copied. Now let's open Zoom. There you go, I think. No, I did something weird. Chat. I just sent the link. So, any questions? Anyone? Right. So, so if there is any question, please feel free to ask. So now we have did some kind of a primer on Grassmannian, and now we'll see how it is relevant to what we were like to vector bundles itself. Okay. So let E be a vector bundle on X. Then E is a subset of X cross W. Right? We have seen that any vector bundle is a subbundle of a trivial bundle. Right? So that means we have EP. So the fiber above the point P is in fact a subspace of W, right? Subspace. And what's the dimension of the subspace? K. Right? So like if this has rank K, then this is a K-dimensional subspace. Right? So given any point P, so now we define a map from X to the Grassmannian K comma W, which will send a point P to basically EP, since EP is a K-dimensional subspace of W, right? So that's a perfectly valid map. Now, one thing to note about this map is just how we can just recover the whole original vector bundle from this. If we pull back the tautological bundle from here, we will get back E. Because if you think about it, the tautological bundle is sitting inside the trivial bundle. And when we pull back, for every point P, you'll get a particular subspace of W. Right? What is that subspace? It is precisely the subspace EP. Because that's how P goes to EP was the map. And tautological bundle, the vector space above EP was EP itself. So for every point, we'll get EP. And so if we pull back, we'll get the map E. So in particular, this is a very nice map, and we can in fact recover the vector bundle just from this data. One thing that we have not checked is the continuity. So I'll just point out how to check the continuity. Again, for continuity, fix vector bundle. Sorry, fix inner product on W, and then we can define the orthogonal projections from W to phi P, from W to EP, right? And then of course which is sitting inside W, so it's a map from W to W, right? So we can take orthogonal projection, right? And the point is that we have this map X, right, to Grassmannian, and then this sits inside endomorphisms of W, right? So to check the continuity, it is enough to check the composition is continuous, right? So for each point we are getting an inner orthogonal projection, all we need to check is that the orthogonal projections continuously vary. So this can be done by saying that, okay, EP is locally trivial. Now we have a locally trivial bundle, like a trivial bundle sitting inside another trivial bundle. Then the orthogonal projections must vary continuously, right? So that's how we can check this. So I'll just pointing out, this is how you check it. And I'm leaving it as an exercise to check. PHECK. Right. Any questions? If there are no questions, I'll proceed. So now the point is, given a vector bundle, we have obtained a embedding into the Grassmannian. Sure. What if we had two different embeddings? Then how are they related? Right? So let phi be one embedding, X cross W, V, and psi be another embedding, X cross V, W. Be two embeddings. Then we can define the following embedding. Okay, so this is a nice trick. We can define T. So wait a minute. So we could obviously embed E inside X cross V, direct some W, right? But this embedding comes in two ways. Like actually there could be three embeddings. One could be like any point here goes to V comma W, like whatever, just psi of T comma 0, Another option that we could have is 0 comma psi, or we could do something like a diagonal in the sense of psi p comma phi p comma psi p, right? So there are like 3 embeddings we could obtain, but the idea is we can in fact draw like a straight line from the first embedding to the final embedding, to the second embedding, which of course which will have this third embedding as obtained at the point half, right? So now I'll explain what I'm saying. I'll formally write it. We can define this map t phi plus 1 minus t psi, which goes from e to x direct sum v. So it's like we had 2 obvious embeddings, right? One embedding being assigned w to be 0, other embedding being assigned v to be 0. And we are saying, okay, just join them with a straight line, right? Join both these embeddings with a straight line. This gives a homotopy between phi comma 0, the first embedding, and psi 0 comma psi, the second embedding. Right. Okay. So now we are seeing some kind of homotopy coming here, that we could, right? So we could obtain 2 things like if we have 2 different embeddings, they must necessarily be homotopic in a sufficiently large dimensional space. So this prompts the following lemma, which will prove. Lemma. Actually, I think I would rather write this as theorem. This is the main theorem, which is right. K rank vector bundles on X is isomorphic to direct limit of X cross G R K comma N. It is isomorphic to homotopy classes of maps from X to direct limit G R K comma N. Right. So this is just some general statement about homotopies, homotopy theoretic statement, that if you take a direct limit of the sets, you'll be X cross direct limit. So what we're actually focused on is the first isomorphism. The second isomorphism is just a general kind of a statement. So proof. So using the arguments that we saw above, that given any vector bundle, we can obtain a map to the Grassmannian, right? Now, if 2 vector bundles are isomorphic, then it would give me different kind of embeddings into Grassmannians. They could possibly give me different embeddings, but those embeddings are necessarily homotopic. So therefore, we have a map vect k x to direct limit x comma g r k n, right? And similarly, because the other side is a single space, we do get a map from x cross direct limit g r k comma n to vect kx, right? So we now, yeah, this is just basically send F to F upper star of the tautological bundle. Take any map F and send it to the pullback by topological bundle. Right? And now, as seen before, and the punch, like the main thing is that these two maps are inverses. Right. So how like is like if we start with a vector bundle and we get a map to the Grassmannian, when we pull back via topological, we get back the same bundle. So one direction, one side, it's obvious that that its identity, and for the other side, what you need to do is you need to say all you need to now say is that this map from vect x to inverse limit this must be surjective, and that's kind of like every vector bundle does give a map. Wait, wait, wait. Right. So like that's all we need to check, right? We have this composite is identity. So this map is surjective. The other one. Right. So I think this is enough. So any questions? I have not properly shown that these are inverses, but yeah, any questions that are there? But this does get the key ideas. And just a name that the direct limit of all Grassmannians, k comma n. Sorry. Right. So is there any questions?
Maybe we can proceed to the next section and take up questions.
Okay. Anyway, so let's. So now we have I will finally start the main thing of the theory that we have been we are here for. What is the K group? So K group is like the thing. Like we have seen examples of K groups since like 6th standard or even before that. So let me give a generalized definition, then we'll do the examples. So let M be a monoid. So just to recall what's a monoid. So we have an operation M cross M to M such that, right, number one, star is associative. And number two, there exists identity. Okay. So this, if we have these two properties, then it's called a monoid. So it's kind of like a group, but the inverse condition is not necessary, right? And in the same spirit as monoids, M is called abelian. if star is commutative. So in the same spirit as groups, we also call M monoid to be abelian if the operation happens to be commutative. So examples would be natural numbers, right? So one thing, my natural numbers always start with 0. So natural number is z greater than equal to 0, right? So the operation for natural number is natural number comma plus, that's one monoid. Groups, of course, are monoids. You know, they satisfy all the axioms and they have extra properties, but they satisfy all the axioms, right? So if we have a ring, let R be a ring, we can completely forget about the addition, and that is also a monoid. So R comma multiplication. We could also do something similar to natural numbers, which is to take natural numbers and take multiplication with them. That's also a monoid. And natural numbers with positive natural numbers only, 0 is no longer allowed, with multiplication is also a monoid. So if you just remove the 0, it still remains closed under multiplication, and so that's also a monoid. So any questions for these examples? So most examples I have given are commutative, which is the case of our interest. Huh?
No, sir, but rings don't really have, in general, have identity, right? So can they be?
Oh, when I say ring, I've always been ring with the identity
Unit.
element.
Okay.
Yeah. Sorry, I forgot about that. Yeah. Thanks for pointing out. So yeah, that's and of course the example that we're really interested in, which I completely forgot, vect x. The vector bundles over x are a monoid under direct sum and tensor. And yes, there is a zero vector bundle. Which we don't usually talk about, but it exists. So now definition. Let M be an abelian monoid. No, we don't need abelian. Let M be a monoid. Then K of M is defined with using the following universal property. Right? For all maps from the monoid to the group, for all maps, for all maps from the monoid to the group, it factors through K of M. So that's the definition. Right? Just a note that we are defining what is a K group, right? There exists unique, right? But we are not proving that such a thing will exist, right? It does actually exist for all monoids, but proving it for non-commutative monoids is difficult. We are only going to deal with the abelian case. Okay. So examples, again, more or less the same examples, right? So we had natural numbers under addition, right? The K group of this is something that we have seen much before, like in school. that the K group is integers. So what we really want is a group which kind of extends the addition of natural numbers, but also has inverses, that is negative numbers. So that's basically integers itself. A K group of a group is just K group of group G is G itself. Something trivial, right? K group of a ring with multiplication is 0, right? K group of natural numbers with multiplication is also 0, and the reason they are 0 is because 0 exists, right? 0 is a very bad element for multiplication, which basically turns everything into, when we turn things into K groups, it just kills everything into and compresses everything into 0. And so if we do remove 0, right? So if we have natural numbers, positive natural numbers, and multiplication, that will give us fractions, positive rational numbers. So again, examples that we have seen in school. Okay. Any questions? If M is an abelian monoid, then Km exists. So proof. So do people here remember, like, kind of how do you, if you have natural numbers, how do you construct integers from that? What we are going to do is exactly the same, like almost the same. There is like one technicality which I'll point out, but everything else is the same. So what we wish to do, right? So keep that example in mind, how to construct integers out of natural numbers, right? So we wish to define a group whose elements look like A minus B, right? If A and B are in. So we define K of M to be M cross M modulo some equivalence relation, right? What's this equivalence relation? AB, which I'm going to think of as A minus B. In fact, after this proof, I'm going to every single time write of it as A minus B, right? Is equivalent to C comma D, C minus D. So A minus B is equal to C minus D if and only if A plus D is equal to B plus C. This is what you would usually expect, right? But there is a catch here. This equivalence relation as defined, this relation as defined is not transitive, right? And so it's not enough. So this is not transitive. So we add this extra T. So T plus A plus D is equal to T plus B plus C. Let me do this one. Like write it properly. T plus A plus B is equal to T plus A plus B is equal to, I think erase this. Why am I overwriting? T plus B plus C, right? Now this becomes a this becomes a proper equivalence relation and we can go more to that, right? So now all we need to check is that this satisfies the universal property, and that's kind of easy because if we give a map from M to G, then we can uniquely extend it from Km to G by sending, if this map was phi, then A minus B goes to phi A minus phi B, right? Or phi A times phi B inverse, if that's what you want, right? So again, all we're really, so the only thing, so this, the way we have defined, it's kind of obvious how to extend it, and it always extends uniquely. So at least the universal property is easy to check. So all we are left to check is that this thing is a group, in fact. So that will follow because if we just take A minus B plus C minus D, that will be equal to A plus C minus B plus D, right? And that, so from here we can see that this will prove commutativity, associativity. Yes, commutativity because we assumed monad was abelian. So commutativity, associativity, right? Identity will be just 0 minus 0. And inverse is the only thing that we did not have before. So the inverse of A minus B will be B minus A. This, if you just add, would be equal to B plus A minus B plus A, and we have just, and we defined that to be 0 in the equivalence relation. So this we have now checked that K group is in fact a group and satisfies the right universal property. So any questions?
So what is that T that you have written there?
Oh, acha, 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 acha. Oh, so T is some element in it for
M.
some T in M. Yeah, that's that. In case you have ever seen localization, this is what we are doing. So any other questions? So let's begin with the definition of what we want, like what we have been aiming towards. The K group of a topological space X, right? So so that we define as the K group of the vector space, vector bundles over X. So that's the definition. Okay. As this has multiplication. So does this Kx, and therefore Kx is a commutative ring. So the multiplication is commutative because the vectex commutative multiplication is tensor, which is also commutative. right? So this is kind of more like an exercise that check that the multiplication of vectors descends to it. So anyways, let's finish this. So now some notation. Class of E, right? E in Kx. Kx denotes class of E in Kx, right? Right. Another notation that we are introducing now is that n bar is trivial bundle. Trivial bundle of rank n. Okay. Right. So in particular, this would be the class of the trivial bundle. Okay. Oh, right. Another interesting point to note is that remember that if we had a map F from X to Y, right? F upper star gave us a map from vect Y to vect X, right? Now we can compose this to give a map to Kx, of course. But now we have a map from the monoid to a group, right? And this must factor through the K group. So we now factor through this to this, right? This, of course, by abuse of notation, we'll also write as F upper star. And this is a ring homomorphism. Because the above thing preserved addition and multiplication, this will be a ring homomorphism. Right? So this case is a functor, is a contravariant functor. K is a contravariant functor. From where to where? From topological spaces to rings. So now let's do lemma. If A belongs to Kx, then A is equal to E minus trivial bundle, class of E minus class of trivial bundle for some E. Some E in vector X. Right. So right. So the proof is kind of easy, right? Note that E minus F. So we know that every element A looks like E minus F. But now we appeal back to the things we proved via Grassmannian. We know that there exists some vector bundle G such that F direct sum G is trivial. We have proven this before, right? So in particular, we see that A is in fact equal to E plus G minus F plus G, right? So this is in fact equal to E direct sum G minus a trivial bundle as needed. Okay. So note, right? So this is like a nice kind of identity. We just proved that any element always looks like a vector bundle minus a trivial vector bundle, right? Which we'll also use in fact. So note, if A E is in fact equal to F, right? Then we know that this implies E plus T, no, sorry, E direct sum T is isomorphic to E direct F direct sum T, right? This is basically how we defined the equivalence relation, right? So so these two are equal, but we can always choose a complement of T so that it becomes trivial. So, right? So this is if and only if E direct sum some trivial vector bundle is isomorphic to F direct sum the same trivial vector bundle, right? So such things are called stably isomorphic. Okay. So just an example of a non-trivial example of stably isomorphic bundles. So in fact, what I'm going to give an example of a stably trivial bundle example. So for this example, we're going to take the field to be real numbers. Right? Consider tangent bundle of S2 and normal bundle of S2. Right? Now, one thing to note is that normal bundle of S2 is in fact trivial. We can check this, not very difficult. One obvious way to see is that the normal bundle has this it has a constant section, right? It has a non-trivial, non-vanishing section. So therefore, normal bundle must be trivial because it's of rank 1. On the other hand, the tangent bundle does not have such a section by Hairy-Ball theorem. So this is non-trivial. Again, on the other hand, this guy is trivial. Okay. But tangent bundle of S2 direct sum normal bundle of S2 is isomorphic to, this is like a general identity, tangent bundle of R3 restricted to S2. Right. Right. And so, yeah, so this is just, and tangent bundle of R3 is trivial. So this is in fact just S2 cross R3. Right. So this is trivial. Right. So therefore, tangent bundle of S2, class of tangent bundle of S2 plus class of 1 is equal to class of 3, which implies class of tangent bundle of S2 is equal to class 2 of trivial bundle. So this gives an example of vector bundle, which is two vector bundles which are not isomorphic, but they are in fact stably isomorphic. Okay. Hmm. Give me a second. Any questions? Then I'll move into the next topic. Really. So please ask questions. Okay. It seems that there are no questions. So I'll proceed. So definition. Right. So note that given any space, we always have a map to a singleton point. Right. Star represents singleton point. Right. So we always have the constant map. There is only one map, and that's the constant map. Right. So I don't know what to call this. I'll write this as right. But that this thing will always induce a map from this thing induces a map from K star to Kx. So one easy question, what is K star? So, okay, what are the vector bundles on a point? They're all trivial vector bundles. All right. If they are all trivial vector bundles, so that means the vector bundles are decided completely by their rank. Okay. So if they're determined by their rank, they must be, what is it called? They're basically natural numbers. And the moment you take the K group of natural numbers, you'll get integers. So that means this is integers, right? So that's nice. At least we get this. And what about the other guy? Okay. So that's good. So we have this nice map from integer to this. Now, suppose, right? Not suppose. So now what we are saying is, we define K tilde of X to be isomorphic to, so not, is a definition. So the definition is just the kernel, not kernel, co-kernel, same thing. Co-kernel of this map. Map K star to Kx. Okay. So K tilde is defined as the co-kernel. Now let us continue from there. We also define rank map Kx to Z. Right. So now if X is connected, right? If it's not connected, then we always did assume X is connected, but right, this I'm just pointing out that this is being used here. Otherwise, also it is possible to do, but it's not that. What should I say? Actually, you know what? I won't even take this. I'll just directly do the way. So take inclusion of a point inside X. Then we get a map, again using this contravariance, we'll get a map from Kx to K star. So we have this map K star, the first map that we got, right? To Kx to K star, right? So this could be some point, and this is a choice of points. So if X is connected, then the choice doesn't really matter. But if X is not connected, then this choice actually matters. And this is Z, right? This is Z. And the point is, if we start with a vector bundle, the pullback will be trivial. But the pullback onto the point will just give me back the exact same dimensional vector space on star. Right? So we start with a trivial bundle, we end with a trivial bundle. So we see that this map is what should I say? This map is identity. And that gives us that this thing is canonically split. So therefore, Kx is in fact isomorphic to Z direct sum K tilde X. This splitting is canonical if X is connected. Otherwise, it depends on the choice of connected component. But it is still possible to easily break it. So theorem. So we kind of homotopically classified what vector spaces of rank can look like. And kind of one aim that we have is to give a very similar classification for Kx. Right? And we could then use that classification to compute the K groups, at least some examples. Right? So I'll properly do how to get to that classification. So kind of like classification space for first K tilde, and then I'll just easily get the classification space for Kx. So theorem, K tilde X is in fact equal to direct limit vect nx. Okay, so this kind of stems from a very nice observation that any element in K tilde X looks like a class of E minus a trivial bundle. I think since Kx looks like this is a quotient, so it will obviously be a class of these guys, right? But Kx is by definition, K tilde X is by definition when we went modulo trivial bundles. So that means this guy is in fact 0 in K tilde X. So any element of K tilde X looks like class of a vector bundle. That's what we have concluded. Right? And and E is equal to E direct sum 1, E direct sum trivial bundle in K tilde X. Again, same argument. The 1 is not useless. So so if we were going modulo this equivalence relation where we would take a vector bundle, then vector bundle direct sum trivial is same as the vector bundle, right? That is same as saying vect x, vect nx to vect n plus 1 x. E goes to E direct sum 1, and then we take the direct limit of these maps. So this is the maps via which we are going to take the direct limit. Okay. So now what we see is we have a map from vect. Wait a second. Right. From vect nx to k tilde x, we have a map, namely E goes to class of E, right? And we see that if we go from E to E direct sum 1 in n plus 1, it defines the same class. So in particular, what we end up with is that we in fact get a map from direct limit, right? Direct limit to kx, k tilde x. Okay, so now I need to, right? So this is one map. Now, one thing to observe is that direct limit, so this direct limit nx is a group under direct sum. Why? Because if we have an E, then there exists F such that E direct sum F is trivial, right? But we know that, right? So it's trivial, but kind of like this trivial is like all trivial bundles have been taken under the equivalence relation here, right? So vect nx is inside vect n plus 1x by identifying the trivial bundle here and there, right? It's like E to E direct sum trivial is identified. As a consequence, all trivial bundles are identified. So this is in fact equal to 0, trivial bundle. So this is a group, right? So now because this is a group and K group is defined by universal property, right? We can use this kind of an argument. So we have vect x to direct limit n vect x, right? Then from here we have a map to kx, right? Here we have a map to k tilde x, right? And then we have maps like this, right? So we obviously have a map like this, which we have shown just now, right? And we have a map in the reverse direction, right? Why? Because from vect, if we have a map from vect x to a group, that will factor through kx. But this map will end up sending all trivial bundles to the 0 trivial bundle because all trivial bundles have been identified in the direct limit as we just saw. Okay, that means this map in fact factors through k tilde x, right? So we have this map, and now using the fact that these maps are surjective, vect x to k tilde x is surjective. Every vector bundle looks like class of E, as we saw. And similarly, this map is surjective. We can, and the diagram commutes, like both the. So corollary, the classification that we were here for. K tilde x is isomorphic to direct limit over K x comma G R K comma infinity. Right? And this is in fact then isomorphic to x comma inverse limit K G R K comma infinity. Right? Right, this is just right. So this is a corollary. And there is a nice name for this. So this is called so direct limit if if x is equal to if the field is K, if the field is equal to C, then this direct limit K G R K comma infinity is called BU. Right? Okay. So, but the real problem with, and also,
that space should be vector n x, not limit direct limit of vector n x.
oh yeah, sorry, vector n x. Yes. Thanks. So now we are ending towards the lecture, which is right. So but we don't really understand the Grassmannian, at least as of yet, right? What we do understand is the GLN, right? We have some vague ideas about GLN how it works, right? So another corollary, which is of course, particularly in the case when the field is equal to C, again. So K tilde of the suspension X is equal to limit X comma GLN C, which is isomorphic to direct limit X comma UN. So this is a general known fact that GLN is homotopy equivalent to UN. That's all I'm using here. And then we can take the direct limit and get X comma U infinity. Right. Or I could take X comma GN infinity. That's also completely. I could take the direct limit inside, right? So I'm just calling these things. I'm just giving these a name, but they're basically just a direct limit, right? And yeah, that's nice. And another corollary that I just want to mention, just for the sake of completion, is classifying space. Kx is Z cross Bu. So basically, we need this extra Z that we need to get from somewhere. Remember, because Kx is just Z direct sum Bu. Z direct sum K tilde. We know K tilde will come from Bu. So we just added this Z here. Like kind of something stupid, but sure. Right. So anyways, this is the important corollary because we kind of know what the homotopical behavior of JLN is. This we can use to compute vector bundles on spaces, right? So for example, S2, right? Which one can also think of P1C, by the way. Just wanted to mention that, right? But S1 is a suspension of S1, or S2 is suspension of S1, right? So we have K tilde of S2 is homotopy classes of maps from, right, is direct limit n x comma gr, not gr, no, we are talking about gln. So this is S1 comma gln c, which is homotopic equivalent to, so this is just the fundamental group, right? So we are basically trying to compute the fundamental group of glnc, but it is the same for every n, which is z, right? So this is in direct limit of z, which is just z. So we now know that k tilde is z. K tilde of S2 is equal to z direct sum z. Sorry, k tilde is equal to z. K is equal to z direct sum z. So, but one thing to note is that I have not been able to compute the ring structure here, right? So that's one problematic point, which I'll leave as an exercise, right? And but we do know that K of S2 is. Another thing to note is that if we knew the homotopy groups of GL and C, we would be able to compute this for higher and higher SNs, right? So that's just a point, just a point I wanted to make. And another thing that we have in fact unintentionally proved is the following. We have proved that homotopy classes of maps from suspension BU, this would be just the K group, which is X cross loop space of BU. If you have ever seen the suspension and loop space adjunction, we are using that here, which is then saying that this is, but we already know that this value is same as X cross U infinity. This we know is same as X comma U infinity, right? So this implies loop space of BU is isomorphic to U infinity. So that's all. This is just an observation I wanted to make. More importantly, we have done the calculation. So that's where I want to end the lecture. Any questions? Anything so far? Homotopy equivalent, of course. Any questions throughout the lecture series? Anything?
Thanks a lot for this wonderful lecture. Actually, in the last few corollaries, you have hinted towards some of the next coming lectures. For example, as a generalized cohomology theory, you'll see that BU is actually the as the spectrum of VU is actually going to be the Brown representation of the K theory as a generalized cohomology theory, or let's say Bott periodicity is coming
Bott
up.
periodicity is
Yeah.
coming up.
Yes, we have given a lot of hints through this colorized. Thanks a lot for that. Apart from that, are there any other questions or comments or feedbacks? All right. So if not right now, maybe you can reach Dr. Mohit at any point of time over email.
Sure.
So we'll stop recording.